Okay guys, next up is gravitational fields, which is a really important subject to get your head around, because fields is a topic that is going to come up again later on. So you're also going to look at electric and magnetic fields, and both gravitational fields and electric and magnetic fields have got an awful lot of things in common, which means that if I were an examiner and I was told I had to assess people in a synoptic manner, I might be tempted to ask questions that lump those two things together because they are very similar. I would also expect them to ask you some comparison type questions between two sorts of fields as well. So that's going to be something you're going to want to keep in mind. So before we can talk about gravitational fields, I need to make sure that you've got your head around the idea of the gravitational force. Now I know that during your AS year I spent a lot of time telling you that if you were ever tempted to talk about the force of gravity, what you really wanted to be saying was the weight of an object, because it means that you would always be correct in the exam, and that's still going to hold true here. Now when we're talking about gravitational force, we're talking about the attractive force that's exerted between objects because of their masses. Now gravitational forces are between any objects with mass, and it's caused by the mass, and it is always an attractive force, and that's very special about gravitational fields, that they are only attractive. Now weight is kind of a special case of the gravitational force. Weight is the name that we give the gravitational force that's exerted by a planet or a moon on another object. So weight is a very special case. So again, I'm still never going to say gravity is a force. I might talk about a gravitational force. So just be careful of that. It's a little quirk of language that can make the difference between being right or wrong. And as you know, that can make the difference between getting a mark and not getting a mark. So that's the gravitational force. So we need to think about what is a gravitational field. Fields are really important concepts in physics, and physicists quite like the idea of fields. I'm going to stick another link to another video on here that's got a real nice explanation of it, particularly in reference to electromagnetic fields, but there's no harm in watching it now. So it's going to be a really interesting one. So if you watch the other video, it'll give you a much better explanation of them. Plus it has strawberry cheesecake and cats in it, so it's got to be better than this. As far as we're concerned, a gravitational field is just a region within which an object would experience gravitational forces. So basically every object that has mass can exert gravitational forces on any other object, and that area around it in which those objects could experience that gravitational force is the gravitational field. Now there's a couple of traditions, sort of, about how we represent gravitational fields, and we always draw them by showing lines of force, so like these ones here, or for our planets around here. Basically the difference between these two pictures is showing you that from the planet all the gravitational field lines move towards the centre of it, but if you zoom in real close to the surface it looks like they're perpendicular to the surface, which is why we're not walking around at funny angles. Now, with these arrows, there are a couple of things that are important. The direction of the arrow shows you the direction that the force will act on the mass. Now, that's pretty easy with gravitational fields. You will have to think a little harder about it with electric and magnetic fields. With gravitational fields, it's just the direction that the mass would go because of the field. And as a convention, generally, if we want to show that a field is stronger, we'll put the lines closer together, and if they're further apart it tends to mean that they're weaker. Now that's not a hard and fast rule, it's just a convention. So generally speaking, when we want to show that there's a larger gravitational force somewhere, we might show that the field is stronger by drawing more lines closer together. Again, it's just a convention, so don't get too chained to it, but it is something that you will see. Okay, now we get to go back to something that we should know really well. Gravitational field strength. G. We use G an awful lot already, so we should know this already. And G is just equal to the force that acts per unit mass, which shouldn't be something that you're terribly unused to yet. should be very familiar. Basically what I'm saying is that G, gravitational field strength, is equal to force divided by mass, or F over m. So the unit of this would be newtons per kilogram. I knew it was on the tip of your tongues. Or you can get brownie points if you're also going to say meters per second squared, because those two are exactly the same when we get down to brass tacks. But the newtons per kilogram should be the easy one because it's force, which is newtons, divided by mass, which is kilograms. So newtons per kilogram, easy peasy. Something else we should instantly know about gravitational field strength is that it is a vector quantity. So the direction absolutely matters, and it will be in the same direction as the force. And the G that we're most used to is 9.81, which is Earth's sea level average. Remember, it is just an average. It does change. So if you go up a mountain, it will change quite significantly. But that's the number that you should be used to using. But G could now mean another force. So you've got to think about where we are and what's going on. So for instance, G on the moon is 1.6 newtons per kilogram. Okay, so hopefully there's nothing new there. The new thing that we're going to meet today is actually very old. It's from 1687. We're going to good old Isaac Newton and his law of gravitation. What it says is basically what we've already said so far, that every particle of matter in the universe attracts every other particle, and the force that they attract each other with is directly proportional to the product of the masses, and it is also inversely proportional to the square of their distances apart. So basically he's saying that we're going to have a stronger force when the masses are bigger, and we're going to have a smaller force when the distance between those masses is bigger. And they're going to follow what we'd call an inverse square law, because it's inversely proportional to the square of their distances apart. So this bit here, the inverse square bit, is really a very important feature of this law. And it's often referred to as being an inverse square law, which is something that you will want to remember for when you start looking at electric and magnetic fields. Okay, so let's see if we can take those statements and represent them algebraically or mathematically. And that would give us F is proportional to m1 times m2 divided by r squared. So F is proportional to the product of the masses, and it's proportional to the inverse, so 1 over r squared. And if I just combine them together, I get F is proportional to m1, m2 over r squared. So m1 and m2 are the masses of the particles, and r is just the distance between them. So if we look at this, there's a couple of things that we can say even when we can't put all the numbers in. So basically, if I doubled either mass, that would double the force. So if you're just given a very vague situation, but you're told that one of the masses is increased, in fact it's doubled, you would be able to explicitly say, well, if that one mass has doubled, the size of the force must also double. And because it's a proportional relationship, we can make those leaps. So another common one might be that we're going to double both the masses. If I double both the masses, I'm going to quadruple the force. And the other thing I could double would be the distance between them. And if I double the distance between them, that's going to quarter the force, because it's the distance between them squared. So if I double it, then it's 4 times bigger on the bottom, which means that it's got to be 4 times smaller what's on the other side. So those sort of making small changes to get the relationship without all the numbers in there is quite a common kind of question. I would suspect they would come up on the multiple choice section, because it's quite an easy one to give you all these options of how does it change if I just make this change up at the top. So something to look out for. So I'm sure you've noticed there is something missing from that equation, because I've still got this proportionality sign in here. So what I want to do is get rid of the proportionality sign and put in my constant of proportionality. So all I've done is change my equation, so now I've got F equals G times m1 m2 over r squared. Now G is my constant of proportionality, and it's called the universal constant of gravitation, and that's it there. It's 6.672 times 10 to the minus 11 newtons meters squares per kilogram squared. So it's just a number, and I know that you all instantly know where you can go and find that number if you're in the exam and you need it. That's right, in your best friend the big book. So it is in there, you don't need to memorise it. It is called a universal constant because it appears to be the same everywhere, regardless of pretty much everything. So it is one of those very rare things, a universal constant. Now you may notice that it is a very, very small number, and that's an important thing, because that number is so small. The gravitational force is only ever going to be of any impact if at least one of the masses is very, very large. So basically kind of the size of a moon. Any smaller than that and the force between those two objects is going to be insignificant, which is something you experience on a day-to-day basis. You are not currently being gravitationally attracted towards your computer. That is because the two of you have very small masses, so can't overcome this times 10 to the minus 11 that comes along with the gravitational constant. So that's pretty important. Now, often in this equation, I've not put it in here, but often there is a negative sign before the g. And that negative sign just indicates that the force is an attractive one. Now, with gravitational fields, we tend not to worry about it too much, because gravitational fields are always attractive. But that is not true of all fields. Sometimes I can have a repulsive force as well as an attractive force. So in those, the sign will matter. Now, all you need to remember is that the negative sign in this instance indicates that the force is attractive. You can think of it as meaning that it's going to make the distance between the two objects smaller. So it's negative because it's making the distance smaller, because they're being attracted to each other. So if you see that negative sign, that's what it means. Remember that very often in physics, the negative sign doesn't mean less than 0. It's telling us an extra piece of information, often about direction, because we do work with vectors. Okay? So the next thing we need to have a look at is how we could calculate the field strength a given distance away from an object that's creating that field. So for instance, if we were looking at the space station, what's the amount of gravity that they experience at that distance away because of the Earth? So that would be the field strength at that specific distance away. So to do that, we need to have a little bit of a play with algebra. It's unlikely they will ask you to do this. You will just need to use the final consequence, but I'm going to show you anyway because it's useful to see where it comes from. So I'm going to start with the equation that we are already quite familiar and happy with. So G, as in the gravitational field strength, is F over m. So in this instance, I'm going to say that where m is the mass that's feeling the gravitational force of a much larger mass. So for instance, U, if I want to find out gravitational field strength of U, on you, I'd look at the force that's being applied to you by gravity, and then divide it by your mass. So this is telling me about the gravitational field that a small mass is experiencing because of a bigger mass, which can lead me to rewriting Newton's law of gravitation. So I can now rewrite it so that it looks like this. So F equals minus G, big M, little m, over r squared. So now what I've done, instead of having m1, m2, I've said, okay, I've got my big mass and my little mass. That's all I've changed. So I've still got two different masses. I'm just saying one of them is significantly bigger than the other. Next thing I'm going to do is substitute F from this equation into this one, which will give me, if we just shuffle it around, that G equals minus G big M little m over r squared times little m. So I can basically cancel out my m's, I'm sure you instantly saw that, and make it look a bit nicer, which gives me that the gravitational field strength is equal to minus the gravitational constant times the mass of the object creating the field divided by the distance squared away from it. So if I want to know what the gravitational field strength that the ISS would experience, so the International Space Station. I'd find out how far away it was, and that's the distance I'm going to plug into here. And my big M would be the mass of the Earth. Then just use my gravitational constant, that I can figure out what the gravitational field strength would be at that distance away, so however far away the ISS is. If you're interested, do the calculation yourself, because you can now. So that's it on gravitational fields. Like I said, it's a really important topic, and we're going to look at applying it quite a lot more. Hopefully you'll all get super excited about this one, because it's sort of the start of the really boring space stuff that you all enjoy. But it is a really important topic. And like I said, make sure you watch the video that I've put under this one. It's minute physics, which are always good videos. Okay, so remember, any questions, ask me when you see me in class.